All right, good afternoon, good morning, good evening, good night, depending on when you're watching this video. If you watch it on Monday, happy Thanksgiving. So we are going to work through exercise number 5 of lecture set 6, which is on slide 25. So in this example, we are putting together everything we've learned from lecture set number 6 to study the sampling distribution of the sample mean under various sample sizes when we don't actually know anything about the generative population. So here we have, suppose the mean salary of public classroom teachers is $55.4 thousand. Assume a standard deviation of $9.2 thousand. Notice that there's no information about the shape of the population given. We only know mu and sigma. Okay, so we can make a couple of notes. We can write mu equals 55.4. Sigma is 9.2. And the variable is salary. Right? So just a few quick notes off to the side here. I'll move them down slightly, but I don't want to take up too much space of what we do know. So in part A, it says, and actually we'll also make a note, distribution is unknown. So that's what we know, and one thing we don't know. So it's an unknown distribution. I just mean when I say unknown, I mean we don't know the shape of it. We don't know how to classify it because it's not told to us. We can't assume it's normal. It's most likely right skewed. That would be my guess. Salaries are typically right skewed, but we don't know. So in part A, it asks for us to determine the sampling distribution for samples of size 15. Okay, so we want the sampling distribution of sample mean when n equals 15. All right, so there's a few things that we can write down. First, we know mu x bar equals mu, sigma x bar equals sigma over the square root of n. And then we can say, for example, the distribution slash shape will be similar to population distribution. Okay. So because the sample size is only 15, the only thing that we can say here is that the shape of the distribution is similar to that of the population. But we don't know what distribution it is. N equals 15 is not enough information for us to state that the sampling distribution is approximately normal, because the central limit theorem requires that we have at least 30 observations for that. So all we can say is that it's similar. It's going to be of the same, it's going to be, for example, if the population distribution is right skewed, then this sampling distribution when n is 15 will be most likely right skewed, but not as skewed as the population. In terms of the parameters, okay, well, the mean is going to be equal to 55.4 or 55,400, and the standard deviation will be 9.2 divided by the square root of 15, which is 2.375. Right. So when we're asked to determine or describe the sampling distribution of the sample mean, we want mu x bar, the mean, sigma x bar, the standard deviation, and the shape. In many cases, we won't be able to tell the shape unless we know what the generative distribution is or what the population distribution is, or if we have enough information that we can apply the central limit theorem. All right, so part B is the exact same question, except n is equal to 15 now, or n is equal to 50 now. Okay, so we can take our work from part A, and we can just adjust it. Because again, whenever we're asked for the sampling distribution of the sample mean, we're being asked for these three things. All right, now, the only things that are going to change with our changing sample size are the standard deviation and now the shape. So first off, the mean is exactly the same because mu x bar is equal to mu. The standard deviation is sigma over the square root of n. We've increased our sample size to 50. So now our standard deviation of the sample mean is 1.301. And our shape is going to be approximately normal because n is greater than 30. And then I'll write C central limit theorem. So in part B, just by increasing the sample size, we can now write down what the shape or the distribution of the sample mean is. So we know that due to the central limit theorem, or because of the central limit theorem, the increase in sample size to 50 meets the criteria that n must be bigger than 30, which means that we can now say that the sampling distribution of the sample mean is approximately normal. So given that the sampling distribution of the sample mean is approximately normal, we can now work with this sampling distribution using our techniques established for normal curves. So for example, in part C, what is the probability that the sampling error made in estimating the population mean salary of all classroom teachers by the mean salary of a sample of size 50 teachers will be at most $1,000? All right, so in this context, at most actually means within. So like we had seen in a previous illustration, if we sketch our sampling distribution, okay, so we have something normal like, since n is equal to 50, this is going to be 55.4. What we're asking is, if I move $1,000 in either direction, so this is going to be 56.4, and this is going to be 54.4, okay, then what I want is this red shaded part here. So this question is basically just saying, or is saying, what is the probability that mu x bar minus 1,000 is less than x bar is less than mu x bar plus, well, actually, sorry, it would be mu x bar minus 1 because of the scale we're working on. We've established that the mean is equal to 55.4, which represents 55,400. So units of 1 are our units of $1,000 on this scale. But we could do this in terms of the original dollar scale and just write mu as 55,400, and then we could ask the question directly as well. That it'll return the same answer. I'm just working on a scale where I've divided everything by 1,000. So this is the general question that I'm asking. I want to be at the error that I would like to observe is at most $1,000. So that just means within $1,000 of the population or of the mean of the sampling distribution. So in this case, within 1 unit of that mean. Okay, so this becomes via some substitution, mu minus 1 less than mu plus 1. Okay, so mu is 55.4. So now I have 54.4 less than x bar less than 56.4. All right, now I have to standardize my limits. So we know how to do this from our previous examples. So Z1 is going to be x bar minus mu over sigma divided by the square root of n. So that's going to be 54.4 minus 55.4 divided by 9.2 over the square root of 50. Okay, so that gives negative 0.77. Okay, just make sure that that's the case. Okay, and then Z2, which is the upper limit. This is going to be 56.4 minus 55.4 divided by 9.2 over the square root of 50, which is positive 0.77. So this thing becomes probability negative 0.77 is less than Z is less than positive 0.77. So this is the probability Z less than 0.77 minus the probability Z is less than negative 0.77. We go to our standard normal table. Okay, we look up 0.77. That gives us 0.7794. Okay, we look up negative 0.77. That gives us 0.2206. Right, and therefore we have 0.588. So then we can say the probability that the sampling error made in estimating the mean salary of all classroom teachers by the mean salary of a sample of size 50 will be at most $1,000 is 55.88%. So I would say the probability, or there is a 55.88% chance that the sampling error made in estimating the mean salary for samples of size 50 is $1,000. Okay, in part D, it asks us, why would the approach in C not be valid for samples of size 15? Okay, so the approach in C is only valid because the central limit theorem gives evidence that the sampling distribution of the sample mean when n equals 50 is approximately normal, right? So because the central limit theorem tells us that the sampling distribution of x bar is approximately normal when n equals 50, we can use our standard normal table approaches. But in part C, we don't know the distribution of the sampling distribution of the sample mean. Okay. So however, when n equals 15, we do not know the sampling distribution of the sample mean. Okay, so when n is equal to 15, we don't know what the distribution of the sampling distribution of the sample mean is. So because we don't know what that distribution is, we can't use the standard normal table or techniques built off the normal table, because then we might be looking for the probability in the wrong place. We can't use techniques that require the variable to be normal, right? So we're only allowed to take the approach that we took in C if we have evidence that the variable we are working with, so for example, the sampling distribution of the sample mean, is normally distributed. If there's no evidence of this, we could assume it, but in situations like the one that we're working with here, where we're talking about salary, which is typically not a normally distributed variable, we're most likely going to be looking for a probability in the wrong place. So unless we have evidence that the variable is normal, which we do when n is greater than 30, we can't use techniques built off the normal table. All right. So as always, if you have any questions, please let me know.